Hey, welcome back to my shop. Today we have a job to do for a fellow machinist, and he's running a small shaper, but the machine is missing its ratchet wheel for the auto feed. So we're going to make one out of O2 tool steel, harden it, and do the finishing touches after hardening so it will last a lifetime. We will also take a look on my gug shaper, so you see what the ratchet wheel is doing, and yeah, then we're going to make the wheel. So let's begin. Okay, we're over at my gug shaper, and this is how the ratchet wheel looks on almost every shaper that you find that has a mechanical feed. The ratchet wheel looks like a gear, but the teeth don't have the involute shape of a normal gear, but they have square or trapezoidal shaped teeth where a pawl can engage. You can see on the gug shaper that the cross section of the teeth is trapezoidal. So this lever up here engages the pawl, a ratcheting pawl that engages the ratchet wheel down here. When we move the shaper, it can skip over the teeth in one direction, and once it changes the direction of the stroke, it will carry the drive, the feed screw for the cross traverse of the shaper, just like this. And on the end of the travel, when the direction changes, it skips the teeth, and you can change the feed direction with the lever. You just spin the pawl 180 degrees around. It's a very basic system, but it works fine. And in this position, it's disengaged. So what we're going to make is this part. I already checked it. It's hardened, but not super hard. It's about 50 to 55 Rockwell C hard, so it doesn't wear out when the ratchet pawl clicks over the teeth. So we're going to harden it too and draw it back to 50 Rockwell C. So we have a pretty good drawing of the ratchet wheel that we're going to make. The tooth space needs to be 1.7 millimeters wide. Of course, I don't have a 1.7 millimeter wide end mill or diameter end mill or 1.7 millimeter wide wheel cutter, but I have a 1.6 millimeter wide one, and we'll just take a cut, offset it slightly, take a second cut until we get 1.7 for each of the teeth. It's a little bit of extra work, but should give very good results. I could also grind a fly cutter, but I find fly cutters to cut heavy profiles into steel quite annoying. I prefer to use a multi-tooth cutter for this. I also have a chunk of 12842 tool steel, which is O2. They're going to use because it's easy to harden and doesn't move very much. And the rest is pretty simple work. Turning the outside shape, boring, cut the keyway on the shaper, 6 millimeter wide. We will leave some allowance on the bore. We will make the bore 0.5 of a millimeter smaller, and we will hard turn it after hardening. Of course, we will cut the teeth before we harden it. This is not a carbide wheel cutter. So I took the piece of tool steel, checked about up in the 3-jaw, and I machined the first side of the sprocket wheel. Outside diameters are finished. The bore has 0.5 millimeters allowance for hard turning. So now we'll break all the sharp edges so we don't cut our fingers open. Flip it around and machine the second side. Okay, I turned the second side and part is to dimension now. Next step is to cut the keyway into it. And we're going to do that on the shaper. That's the setup we're going to run on the shaper. I strap clamped the part against an angle plate, so the bore of the part is pretty much centered over one of the slots in the angle plate to give me clearance when I go through with the tool. That's the setup over on the shaper. I took the angle plate with the part clamped to it over to the machine. I prefer to do such a setup on the bench because you don't have to fight gravity all the time, because you can have the angle plate on its back and work vertically. And I brought it over and aligned it with the travel of the cross slide on the shaper. Machine is all set up to cut the keyway. I have a 5mm wide slotting tool here and the slotting tool holder, which does not clap away like normal clapper box. And now we need to center the cutting tool in the bore. And there is a very easy way to do that I will show you. I think I showed it previously, but I will try to go with the camera looking into the bore so you can see what's happening. Okay, you're looking down into the bore of the part, and this thing on the end here that you see, that's the cutting edge of the slotting tool. Now we want to align it so it's centered in the bore. And the way I like to do it, I let the tool contact the part and by taking a very shallow cut, I can see if the tool is centered. I'm going to manipulate the table side to side until I take 2 equal sized chips on both sides of the cutting tool. So in this case I need to move the table over a little bit and try again. And this looks pretty darn good to me. I have to offset the tool 0.5 millimeters to each side anyway, because I need a 6mm keyway. And this is a 5mm tool. But should work out fine. I will take an indicator to the table so I can follow my movements. Add some cutting oil. Okay, we cut the keyway 5mm wide, so now we offset the table 0.5mm to each side. Okay, I had to do a little bit of handwork with needle files to get the fit of the keyway perfect, but now It's a nice sliding fit with a 6.02 millimeter gauge block. That's what I wanted. Just like this. When you step over the tool on the shaper to either side to open up the keyway, the tool tends to get deflected, and you have to take that into account. The keyway will get a little bit of bell mouthing on the end, and that's what I removed by filing. Just a little bit of hand fitting. Didn't take more than 5 minutes. Using a larger Swiss needle file with a safe edge and some smaller fine cut needle files. I also deburred the edge of the keyway and balled over the corners, so nice to a touch, just to give it some workmanship. Choosing the right index plate for this job, we need 30 divisions. The rotary table has 4 degrees per full revolution on the crank. 360 degrees divided by 30 divisions gives us 12 degrees between each tooth space, and 12 degrees is evenly divisible by 4 degrees. It gives us 3. That means we have to do 3 turns on the crank for each division. That means, on the other hand, that we can use whatever index plate we want. I happen to choose that one with the lowest hole count, so I don't accidentally use the wrong one. That means that I can choose any random hole on this dividing plate, and I prefer to do that without the sector arms, because they only get in the way when you do full revolution turns. For each division, I just have to pull the pin, do 1, 2, 3, and just make sure that I go back in the right hole each time. And I will also, I always mark somewhere on the rotary table or index plate my direction of travel with the crank, so I don't foobar that. Not that I ever did that. Let's talk about work holding this part. I have a standard 60mm mill arbor in the Morse taper 2 of the rotary table. That's what I'm going to use to hold this part. I turned a thin-walled aluminum bushing that fits into the bore of the part and has a 16mm bore that's very close fit on the arbor. I just turned this in one setup and then parted it off. This can slide on the arbor, and this is just to center it. And we take 2 arbor rings, put them here as a spacer, the part goes on here, and we have a heavy brass washer and an M8 screw. And that's all we need for work holding. I always like it when I can take an arbor to hold an actual workpiece, because setup is quite fast and it's relatively rigid. Even if we have a lot of overhang, in this case we're not taking a super heavy cut. We're just slitting it with the wheel cutter. Okay, I want to get the wheel cutter pretty precise on center height of the rotary table, and I don't know the center height of my rotary table. So I took a gauge block stack and I added gauge blocks until I get a very snug fit under my workpiece. That worked out to be a height of 83.17. Then I added half the diameter of the workpiece. That's my center height. Then I have to subtract half the thickness of my slitting wheel, which is 0.8 millimeters. So I end up with 100.37 millimeters that I need to have from the table of the mill to the underside of my wheel cutter. Then the wheel is on center. Okay, this is my 100.37 millimeter gauge block stack, and it fits very closely under the slitting saw blade, under the wheel cutter. You have to be careful. The teeth on these are staggered to the side. One goes up, one goes down, so you have to take a tooth that's facing down, of course, otherwise you're off by quite a bit. And also careful when you touch down on the gauge block. You absolutely don't want to scratch it. You don't want to scratch it up like this gauge block, which is a used old one. I'm using that because my good set doesn't have an 80 millimeter gauge block. And I put some marker on top of the gauge block, so I actually see when the saw blade is touching before I touch the metal, because the marker has a thickness to itself. Okay, I already cut the first tooth, 2 millimeters deep in one pass with the wheel cutter. I always say slitting saw, but it's a wheel cutter. It has teeth that cut on the side. No problem to take this in one pass. I'm running it at 95 RPM. Could go a bit faster, but this is tool steel and these are expensive, so I don't want to burn it up. So first one cut. Index 3 revolutions on the widen plate and cut the next one. Okay, as you can see, I went around one time cutting all the spaces between the teeth, and I did not end up with half a teeth, so my indexing was right. And I didn't make an error during indexing. That's also nice. It's always annoying when you have a part, you put already quite a bit of work in it, and when you do the indexing, you foobar it. That's really annoying. I came back and went around the second time with a slightly different height setting on the cutter to widen the gaps to 1.7 millimeters. And now we can take part of the arbor. There we go. One ratchet wheel. You need to deburr it, harden it, and bore it to 18 millimeters. Okay, there we go. I have the part in the oven. It's at 860 degrees C. Now we're going to quench it as usual in vegetable oil. And immediately after quenching, I'm covering the oil with a piece of sheet metal so I don't smoke up the whole shop. Oops, catched a little bit of fire. Okay, close the door. Okay, the part is hardened, came out quite nice. It's nice and hard, but not tempered yet. And I used the micrometer to map out the warpage of the part, how much it went out of round, and it just went around and measured the diameter in a few spots. I know that this is not a very precise way to determine the out of roundness, because there are geometric errors that can be out of round but have everywhere the same diameter. But for a rough idea to see what happened, this is okay. And it seems that we went out of round only about 0.02 of a millimeter. The diameter ranges from 26.01 to 2604. Oh, that's 0.03 of a millimeter out of round. That's not too bad. I left material on the ID so we can rebore it nice and round and to size, and the outer diameter of the ratchet is not very critical. Even if it was 1/10 of a millimeter out of round, it would still perfectly fine work. But for me it was more important to have it hardened so it doesn't wear out when the ratchet pawl clicks over the teeth. We will draw it back to about 50 Rockwell C. That's tempering at 350 degrees C. I've drawn back the hardness to about 50 Rockwell C, and I put it in the blasting cabinet and removed all the scaling, and yeah, now it looks very nice and got a very uniform surface. Last step will be to bore out the ID to 18 millimeters. I chucked the part back up in the lathe, and I'm using an indicator with a wide based tip, with a flat tip, over the ratchet teeth to check the run out. With the flat tip I can average out the part. I tried to use a dial test indicator before, and it was just annoying with the ball falling down into the grooves. So this is about 0.02 of a millimeter run out now, but I couldn't adjust it to go away because the part is out of round, so it will be 0.02 of a millimeter no matter what I do. And it's not a problem in this case, as this is just a ratcheting wheel. But I still want the center bore to be as concentric as possible to the ratchet teeth. That's what I checked here. This is the boring bar I'm going to use. It's a 12mm shank, and it holds a 3mm carbide tool in it. It's ground with about 0 degree top rake, about 10 degrees rake to the bottom, 2 or 3 degrees back rake in this direction. Very little back rake makes the tool very rigid, and a little bit of lead angle, which makes it cut a little bit softer. And this works quite well for hard turning 50 to 55 Rockwell C hard materials. There we go. Tool is cutting nice and clean, and it leaves a gold colored chip so we're not overheating anything. I bored the ratchet wheel to final diameter, and I always in between I always checked with the telescoping indicator gauge for the right diameter, and I ended up at at 17.99 all the way through. So my bore is cylindrical and round and runs true to the outer diameter of the ratchet wheel now. And that's all we wanted. And I have a piece of, this is ground 18 millimeters minus 200s. This is some sort of a bearing spacer, and this is a nice sliding fit in here. So I think that's okay. Always keep in mind this is just a ratcheting wheel that gets on the end of a lead screw and gets sandwiched in with a nut and is driven with a key. So it's not an ultra precision application, but I still want to get it pretty darn good. I don't want to send something out that has my name on it and is shabby work. So yeah, the hard turning always works quite well. The tool gets dull pretty fast though, even if it's carbide, but in this case we have also the problem of an interrupted cut, and that's even harder on the tool. I resorted to a depth of cut of 0.05 of a millimeter with a spring pass to get a good surface finish and no taper in the bore. Okay, there we go. That's the finished ratchet wheel, all hardened, aluminum oxide blasted and hard bored to final diameter. Not too shabby, I would I would say. I'm quite happy how it came out. Like the surface finish from the out of the blasting cabinet, and also the surface finish I got on the ID when I did the hard boring. So it goes to show that you can make in a hobby shop with light-duty tools, you can make machine parts that are absolutely up to spec. I would say this is just as good as the part that is on my GUC shaper, done by the manufacturer. You just have to do it. Just try it. It's one step after each other. If you see a complex part, this is not super complex, but just break it down into smaller steps. A small step, step by step. Turning the outer shape of this part, not hard. Drill it and bore it, not hard. Doing the keyway depends on what you have available. On the shaper it's quite simple. You can also do it on the lathe with a parting tool laying flat, and you can run the carriage back and forth to do the keyway, or you can use broaches, what you have available. Or if you're really in a pinch, you can file it. There are a million ways to do it. Cutting the ratchet teeth, also not hard. You just have to do the math and set your dividing head or rotary table up for the right divisions. You could even do it without a dividing head by Mickey Mousing your way through with an angle finder and some way to hold it in a vise and turn it on, but that would get annoying. Hardening, you could even do the O2 tool steel is really very simple to harden. You could even do it in in a barbecue, in a coal grill, and then temper it in your kitchen oven. If you can get it up to maybe 250, 300. I think the kitchen ovens with the self-cleaning function can go up that high. So that might also be a solution for tempering. Yeah, and then the hard boring is also not... It's no black magic in this part. The hard boring, you just need a carbide tool that's nice and sharp. You take like cuts and then you end up with pretty darn good surface finish. So yeah, if you have some machines and you want a part, you can make it, even if you have limitations in your machinery. You can make anything. So thank you all for watching and see you next time.